broadcast is now starting. All attendees are in listen-only mode.
Hi everyone. I apologize for the delay in getting started today. We had a few technical issues with GoToWebinar, so we've been online troubleshooting, so I appreciate your patience. But we do have an exciting webinar set up for you this afternoon. So without further ado, I'm going to go ahead and introduce our speaker for today. We have Mr. Joe Ghislaine. Your subject today is CAC saving you money on compressed air. So Joe has quite a lengthy resume. I'm going to give you a very abbreviated version, but here we go. Joe is the owner and principal of GOE, which is Ghislaine Operational Efficiency LLC. These are a consulting firm and they specialize in green and lean, meaning green energy management and lean manufacturing. Joe has several energy certifications, including the ones you can see on the screen right now. They're obviously one of our own, AEE's Certified Energy Manager, plus a few others that you see there. So part of Joe's career, he worked for Ford Motor Company. Joe was a senior manager while he was there. He was a Six Sigma black belt. And he held many positions in his 31 plus years, including being the Powerhouse Chief Engineer, Corporate Energy Engineer, the Manufacturing Planning Engineer, and most notably, Global Manager of Energy Efficiency Programs. And during that role, he was responsible for developing and implementing energy management programs to reduce energy costs and usage. Joe has also been a part of the Compressed Air Challenge since its inception. He is a qualified instructor for both CAC fundamentals and advanced compressed air system training, and he serves on the CAC board of directors. Joe is clearly very passionate about energy and currently serves or has served on multiple different energy committees, including those that you see on the screen right now. So, Joe, thank you very much for agreeing to be with us today. We appreciate your time and your knowledge and your willingness to share that knowledge with us. And so I am going to hand over control to Joe.
Okay, thank you. When you were going through the presentation, it was still the main screen, so I don't know if there's a show on the screen or not. So let me.
Okay. If you go ahead and you should be able to go ahead and take control now.
Okay, so
that's good.
Okay, so you can see the main slide presentation, correct?
I can see that, yes.
Okay, terrific. I want to make sure it's the right monitors that I've got up. Okay, well, thank you everyone for joining, and again, sorry for the little bit of a technical delay. We'll go through this, and hopefully that, I know we're running behind on time, but hopefully we'll still have time for questions. I can stay a little bit longer with that. I know other people's times may be short, but we will open it up to questions afterwards, and or I can be contacted as well. She already went over a little bit about me, so I won't go over that. But I will go over the Compressed Air Challenge. The Compressed Air Challenge is a voluntary collaboration of the industrial end users, manufacturers in their associations of KGI, distributors, facility operation, consultants, energy research development agencies, energy efficiency organizations, DOE, and utilities. And this group had one purpose in mind, and that was really to help improve the performance of the compressed air systems and help end users learn about it and save money. So really, it's about training. It solves problems and also saves energy. CAC's trained more than 15,000 people since 1999. We have the two levels, which was mentioned, the fundamentals and advanced. We also, for system specialists, have qualified Air Master specialists, and we've also just recently launched the end user awareness training. We also have the best practices manual, which has been updated several times, and it is a one-source manual that addresses all areas of improvement for compressed air and operational efficiency on compressed air systems. So why care about air? CAC cares, and you should, because just an example for the U.S., compressed air accounts for more than $5 billion in energy costs. It represents 10% of the electricity use in North America and accounts for 16 of the all the major motor systems. And this is from the U.S. Department of Energy. So when you go through to reduce compressed air costs, what do we need to go through and do? Well, it's very important to maintain compressed air system efficiency. We really need to go through and understand what the efficiency of the system is, and also to go through and take a best practices approach and use the system approach when doing it. And that's really about what Compressed Air Challenge is all about. The system approach that we take is to, one is the awareness training. This is part of that, but we also have the trainings that we mentioned earlier. Then the real key is to establish a baseline. You want to go through and know where you're at, calculate the cost, and then be able to use it to calculate savings. And it's really important to relate it back to production or whatever the operation does, whether it can also be to, for commercial buildings, it can be occupancy, it can be other things, but it's important to relate it back to that cost that people are used to. You want to go through then and align the supply with the demand. Along with that, you want to start looking at where are the opportunities to improve. So you want to look at reducing system pressure, making sure you do maintenance. It's an important part, especially the repairing leaks. You want to go through and eliminate the inappropriate uses. You want to take advantage of heat recovery. And then you want to use total cost and new system design, and then integrate it into whatever your current processes are. And we'll go through a bit more in each of these as we go forward. So baselining. The process of baselining really involves taking measurements and determining the effectiveness of the operating system for the compressed air. And it's really under various production requirements. And that's going to be to measure the power, the energy, pressure, leak load, and flow. And taking measurements in both before and after changes is really important. And if you think about it, that's important. Why? The real key there, as we know, is to go through and see if the efficiency improvements actually happened. And when you went and made the changes, did you get the results that you expected? And if not, what was the reason? Data should also be taken and collected under normal operating conditions. It should also be other significant conditions as well. We want to look at different production levels. We want to go through and look at seasonal variations, and then we want to look at changes to the operation, whether you've added equipment, taken equipment away, changed processes. You really want to look at that before and after. And the real key for why you want to do that is because you really want to go through and align the supply with the demand. Like any system, the compressed air system is always often called the fourth utility, because again, it's one that you have to go through and produce to go through and make any kind of end use work. It actually is the compressor that's doing the work. So like any other supply system, it's driven by the demands of the system. So the number of operating compressors, both the duration, flow, it's all driven by the end use and the effect of their systems and the dynamics that those systems have. It's really critical. So when we talk about systems approach, it's getting out of that compressor area and the supply side and really understanding what are the demands doing and what is it doing to my system. This relationship really requires the monitoring and control of not only the compressors, but the end uses, because again, if they don't use it, you don't have to make it. So it's really one of the major cost drivers you have in the system. So to do this, you want to go through and to establish a baseline, remembering that the system is dynamic, and you want to go through and relate these to the operational costs in the system that are being and it needs to be developed so you can go through and understand what those are. Like anything, if you can't measure it, you can't manage it. Again, establishing the baseline is key. Looking at flow, which is the output versus the input power in kW, and also developing a pressure profile. These two things allow you to go through and see, one, how efficiently your compressors are working, and two, how dynamic your system is and what's happening in that system. Again, converting the compressed air usage into dollars, It's great as engineers to understand, for us to, and energy folks to understand SCFM, KW, all different types of measurements. But when you talk to people outside, like plant managers, controllers, they have no clue what those are for the most part. And really what they're concerned about is how much is it costing and what is it. So putting it back to what the actual cost of whatever the facility measures is very important. And it also helps drive energy efficiency, because now it puts it in terms that everybody can understand. And, being from the auto industry, design engineers would do a lot to try to go through and take cost out of the vehicle without hurting the quality. This is one way you can do it, and this is another way of showing people what the effectiveness of it is. So once you've done that, you want to take that strategy and you want to make sure you to control and monitor all the compressors and use a good, effective control strategy to do this. In many cases, you're going to want to go through and look at the amount of storage you have, both the primary and secondary. Again, this allows you to meet the peak demands that you have in the system. One of the examples, again, going back to the auto industry, is stamping presses, which require a lot of air to stamp out sheet metal parts. They each have their own secondary receiver on there for being able to help assist anytime that the press is actuating. The next part is demand. So I want to go over the typical components of the demand. When we go through and look at the demand, we have the normal production, which is about 50%. You see the big yellow piece there, which is leaks. That's about a third, or 30% of it. And then we have the other two components here. One is inappropriate uses, and the second is the increased demand due to excessive system pressure. This is often referred to as artificial demand. What artificial demand is it is the requirement that you have of the system to keep a higher pressure than is needed or required at the end use because of effects of what's happening with the system. And the major one is going to be leaks, and that's going to be leaks on your supply side. What happens when a compressed air system leaks? It reduces the pressure. So what do you have to do? You have to crank up the pressure to feed the leak. And then what happens when you crank up the pressure? It leaks more. So it's a continuous cycle. So you'll see how important air leak is and air leak management is to the system in reducing this artificial demand. And then the inappropriate uses, as I mentioned, we will talk about those a little bit more. But really what that is that's being able to take things that we currently have done or have traditionally done with compressed air, and now the technology has changed. How can we go through and use electricity directly rather than going through the conversions to do compressed air? So some of the key things for demand side points, you really want to go through, if you want to reduce costs, you want to get rid of that unproductive demands. And those are the inappropriate uses. They're the leaks. It's the artificial demand. And it's also reviewing those end use requirements. So what's the air quality requirement? If you ask somebody, they'll always want the best quality they possibly can get. But every time you go through and do that and you over clean the air, it costs money, it adds equipment, and it adds pressure drops that go into the system. High pressure applications, going through and sizing and doing the right pressure required for going through and doing it is important to go through and do. You need to be able to understand that. And then also the high volume intermittent demand applications. These are ones that put a lot of load on the system immediately for a short duration of time. And it's an excellent area for being able to do secondary storage to go through and minimize that demand effect. And these are all are also ones that we cover in both fundamentals and advanced. So one of them I want to talk about, though, is system pressure reduction. So for every 2 psi, it's 1% efficiency increase. So anytime you go through, and this can be converted back to bars, back to to standard measurements that you have, but we deal with since a lot of the compressed air challenge material is based from US, we do talk in the PSI, but really it's the reduction is the efficiency. The importance is reducing that pressure gives you the efficiency. So if I can go through and reduce that 2 PSI on a 1,000 horsepower motor running at 80 PSI rather than 100, it would save over $60,000 a year. So this is really important. You might say, well, boy, 1,000 horsepower, that's an awful big compressor. Well, I can also back it off and say it's 100 horse, and then that's 6,000 per year. Either way, it's a good opportunity to look at. And one of the reasons you want to look at what the actual requirements and your demand are to see if there's the opportunity and the possibility to go through and do this pressure reduction in a system. Now, again, you have to be aware of what's happening in the system. You can't just lower pressure because that'll affect production. But the real key is understanding what you need to do to be able to go through and lower that pressure. Often, there's a very small percentage of loads that require higher pressure. One of the ones that I ran into as the energy manager at Ford, we were going through and doing audits, and in the most unusual spot, I was doing one of an office building. We had a North American automotive operations building. It was a 14-story office building, and I was doing an energy audit of it, and of course expecting to find, things like lighting and HVAC, etc. Then I found a compressor that they had running at 90 PSI, to go through and maintain. It was an on-off compressor that was running to maintain anywhere from 85 to over 100 PSI on the compressor. And for actual building heat and the requirement of load that they had in the system, they only required maybe 20, 30 PSI at max. So I asked why, and I found out that the reason they did it was that because whenever the executives came in and had low pressure on their tires, they needed to pump up the tires. So basically they were going through and wasting all of the time and energy to go through and run the equipment at a much larger compressor than it was required. So I had them actually get a smaller compressor and go through and modify the system to be able to take care of that. But it was a very small thing that was driving the loads, and you'll find that a lot in production. Many times the production equipment is spec'd at a higher pressure, either for footprint size or that's what the manufacturer does so they can use smaller cylinders. When you go through and do that, you have to be aware of it because, again, that drives the entire system. So you have to maintain that pressure even if it's a small percentage. And what we're saying is do something about it. So what you want to go through and do is you want to take those high pressure end uses, you need to address them. So if you can, you want to modify the equipment, or you want to go through and add booster compressors or smaller compressors, or even separate it into a separate system, or feed it from one of the supply compressors you have. There's multiple ways of doing it, but the key here is don't let it drive the system. Take advantage of being able to lower those pressures. Maintenance is always a necessary evil. I spent a lot of my career on the maintenance side, and it's an important part. Again, we talked about the pressure drops for lowering pressure. The same is true for the actual pressure drops across the filters, dryers, and any component in the system. Again, that same 2 PSI equals 1% efficiency relates to those pressure drops. Increased temperatures and moisture. So anytime you go through and don't have the proper removal of heat in the system, and you don't have the capability, for example, of the intercoolers and aftercoolers of the compressor to get rid of that heat, it'll put hotter temperatures into our chiller dryers. And when you do that for a chiller dryer, every time you go through and increase it, even from its design set point of 100, the 300 rules in the U.S., which is 100 PSI inlet, 100 CFM, and 100 ambient. So anytime you go off of those design parameters, you'll go through and derate the dryer. So when I put higher temperatures going into the dryer of greater than 100, if I go 20 degrees more and put 120 degrees into the dryer, I will actually double the load. So again, it's very critical that you get rid of that heat. It also reduces the air quality and shortens the equipment life. Inlet air filters to the compressor. Dirty filters reduce the air compressor capacity. And for every 4 inches of water pressure drop across the inlet air, the filter, you'll lose 1% efficiency. So it is real critical that you go through and take care of that. And then, of course, the number one thing is production downtime. That is the most critical thing of maintenance, both on the actual equipment itself and then the effects that it has on production and maintenance if you don't go through and maintain the quality of the air and the quality of the equipment. And of course, the biggest maintenance loss that you have in a system by far is air leaks. Going through and looking at this, the Department of Energy showed that a actual tight system will still have a 10% leakage rate. We like to shoot for, the CAC likes to shoot to push to get between 5 and 10%, because again, as you're going through and fixing them, as you fix leaks, other ones come about. And it's not uncommon to find 20 to 30% leakage rate, sometimes as high as 50%. And air leaks cause really efficiency losses, and it's in several areas. The leak itself, at 10 cents a kilowatt hour, a 1/4 inch air leak will cost over $18,000 per year. If you look at what else it'll do, it also causes you to have elevated system pressures for those unregulated leaks. It's going to cause you to increase the compressor operation, which is not only higher energy costs that we talked about, but increased maintenance. And then also the unnecessary purchase of additional equipment that you have, because many times, rather than repair it, when you start running out of air, what do? We buy another compressor. So that's an important part that needs to be taken into consideration. Inappropriate uses. Inappropriate uses are really anything that you can go through and do with electric technology. The most common one is anytime anybody's using an air motor, that can be looked at for using an electric motor. And why do we want to do that? Well, the overall efficiency of a typical air compressor can be as low as 10 to 15%. The annual cost for a 1 horsepower motor versus an electric horsepower motor running 5 days a week, 2-shift operation at 10 cents a kilowatt hour. For the compressed air, it's $2,330 a year. For the electric, it's $390. So you can see there's a great difference from going through and doing the compressed air because of all of the losses in the system, most of those coming from the heat of compression that you have in a compressed air system. So really going through and looking about what you can do and how you can change and where you're using the compressed air and how is an important part to look at. Some of the examples that I've done over the years for the electric conversions, we had paint dryers on drives on the paint mixers in the paint shop using air motors, replacing those with electric motors. You can get ones that are intrinsically safe, explosion-proof motors, so the concern about fires is not an issue. Parts drying and components plants, again, using it to blow off and dry components. Going through and using blowers is a better way to go through and do it. Air tools themselves, we switched over a lot of times to DC nut runners. It not only gives you the energy efficiency, but in many cases gives you an increased quality. In the auto industry, we had many of them that were safety or delta fasteners that needed to be done, and this would give us feedback that it was at the right torque, so we can prove that there was no issues with the actual deltas that we had. Air blowing in a paint shop, again, trying to get dust off of it, or going through and drying high efficiency nozzles, or better yet, low pressure electric blowers, similar to what you'd see when you take your car through a car wash. Personal coolers, many people have go through and use air to blow on them because they feel it's cooler. I always have a concern, especially with oil systems, it's not very good to be able to breathing that in. Also to cool cabinets, so using vortex coolers. replacing them with fans or AC units for the cabinets really is a good idea to go through and do, because again, you're not going through and blowing the air that has oil and mist in it into either cabinets or a person's breathing space, but it now allows you to go through and get rid of that high cost of energy. Vacuum generation, many times this is used for parts moving, especially in things like stamping or putting in glass windshields where suction cups would hold the panels in place as they're being put in. You can go through, and this is done with a vortex cup where you would run air through it to create the vacuum. Going through and doing those Venturi ones, the Venturi vacuum cups, and replacing them with high efficiency vortex cups or smart pump vacuum systems that just create a vacuum while the system is in, saves a lot of money and a lot of cost on the movement of parts. So those are just some of the ones for inappropriate uses. I want to now talk a little bit about heat recovery. So heat recovery, you can go through and do, again, most of the losses in the compressed air system are due to heat. You got to get rid of that heat, so you might as well use it. So for cold areas, you can use it for supplemental space heating. You can use it for industrial process heating. You can use it for water heating, for domestic and potable water, or for gray water that's used for in processes. You can use it for makeup air heating, and you can also use it to preheat boiler makeup water. So, and then of course, drying of compressed air, you can also go through and use heat of compression if you have oil-free air compressors, to be able to use heat of compression dryers to actually dry it in a desiccant type dryer. So taking advantage of going through is important to go through and do this. Where would you find some of those heat sources? On an air-cooled rotary screw, you can add the ductwork and auxiliary fans to recover as space or reject it outside with the thermostatic controls. Water-cooled compressors and motors, you can install heat exchangers to go through and recover the heat or reject it outside. This can be used for not only heating, but it can also be used to produce non-potable gray water or potable water used for actually domestic hot water. There's cautions you have to do with the type of exchangers you use. And then of course, engine-driven compressors, they also can be recovered from the heat of the engine jackets and the exhaust steam. Gas turbine-driven air compressors can also allow the same thing. The heat can be recovered from them, and either from the exhaust stream to make hot water or steam as well. So again, these give you the opportunity for even additional energy savings through heat recovery. System design is critical, and you want to use at total cost. So the next step is looking at the system. You want to go through and do the benefit. You have to weigh the cost and benefits of each type of the thing and find the most efficient operation for compressed air and the end uses. Because again, we need to look at those end uses and how they're being designed and spec'd to make sure we can optimize the compressed air system usage. So the air compressors themselves, again, the right type and right mix for the demand. You want to make sure that you have good base tilt load units, and you use those for base loaded, like a centrifugal, and then variable loads, you'd want to use VSDs as an example to go through and do that. You want to be able to design the heat recovery, which we talked about, whenever it's cost effective and appropriate. You want to specify the end uses and the operate at the lowest possible pressure. Again, once you get those big uses down, you can go through and start lowering your pressure in your total system and not let those drive it. And then, of course, pressure drops. Designing systems and equipment with pressure drops to minimize that, whether it's across the filter dryers, even piping systems. One of the examples that I have is the system that I had at Chicago Stamping when I was the Powerhouse Chief. We were actually going through and having pushing 25,000 CFM through a 14,000 CFM dryer, and it was actually causing about a 12-pound pressure drop across it, and obviously not drying very well. With that amount of pressure drop and the fact that they were large centrifugal compressors, I was actually able to write a cost savings project to put in 2 new dryers and a building addition for what that costs. Looking at what those are, not only when it's designed, but then after time, because systems are always engineered great in industry, but then I find they grow over time, and it's not always engineered after that. So you have to watch what happens over time as well. Then the incremental cost of increasing you really, many of the times that was acceptable in the past to have pressure drops of 5 to 10 pounds through a large system. That's really not acceptable because, again, you're talking about large systems and large costs. Over time, it's very cost effective, and you'll find that that many times the pipe size can be increased for a small amount of the cost, and that gives you a much better pressure drop through the entire system. And it gives you ongoing energy efficiency and cost savings. So another example of design, 2 stamping presses. They were 2 large transfer presses, same manufacturer. It was one that I had, again, when I was the powerhouse chief. We went to another thing. We just put in a brand new transfer press, and they were saying that they needed 80 PSI. Went to a sister plant that was a joint venture with Mazda and Ford. And they specified the equipment, and they said, nope, it's going to operate at 60. So we had the exact same equipment, but the supplier said that you have to supply it with 80, which meant that they could go through and use smaller cylinders and, more profit for them, where the other one was specified. Because of the plant, the size of Chicago, if I could have gone through and reduced it from 80 to 60 PSI, it would have saved over $300,000 a year. Again, it was a very large compressed air system, but the point being that if you don't go through and ask a supplier what they want, they will give you what is the cheapest for them to do, whereas if you specify it, the cylinders will be larger, but over time, it'll be much more efficient. So some of the design pitfalls, again, this is a real high overview. You'll be able to learn more if you go to the Compressed Air Challenge Fundamentals and Advanced classes, but this will give you a flavor of just some ideas and things to think about that we go into much more detail in the trainings. So when you go through and look at this, when you're starting to do design and design projects, going through and using only full load calculations for compressors, most of the time the compressors will stay in a partial loaded state and not at the full peak load. So going through and just making the nameplate would have you overestimating the savings. Using average cost for kW for off-peak savings, again, if you're going to be shutting down on weekends or on off shifts, it's a different cost structure. You don't have the demand structure that's included. Assuming all unregulated demand when calculating artificial demand, again, if it's regulated, it does not go into that artificial demand calculation. Assuming pressure flow controllers negate the need for compressor control, you still have to control the compressors and understand what the base of those are. Implementing capital solutions before you do the low-cost opportunities. Again, you want to go through and take care of those low costs before you spend a lot of money. Buying only VSDs and or using them as a base load. They are not designed for base load machines, and they are inefficient as a base load machine. So they're very efficient for going through at partial loads. You need to have base load units in your system as well. Not adjusting centrifugal compressors for savings winter and summer. Since it's a dynamic machine, there's a big difference in what they actually produce because of the temperature difference, especially with the large climate changes. And not using utility rebates or government rebates. It's an important part for anybody that has efficiency. So people is the next piece I want to go over because, again, they're the ones that use the compressed air. They're the ones that need to be involved. So what if I told you could reduce compressed air usage and energy by buying jackets, hats, keychains, and pizza? Would you buy it? When I do this, many times people laugh and say, really? Well, that's exactly what the Monroe stamping plant did. The actions that they took, it was an hourly team. The plant manager got the team red jackets so they would stand out. They implemented an aggressive energy awareness and a leak tag program. They gave away buttons, keychains, hats, and T-shirts for reporting and getting air leaks fixed, and pizza for the best red coat energy audit when they would go do their audits on the weekend. They posted leak boards throughout the plant, and they used the Ford Communication Network, which were TV monitors that were in all of the break rooms, so they would broadcast messages throughout the plant. The results is they reduced their usage from 17.4 million cubic feet per day to 9 million cubic feet per day. the non-production usage dropped from 5,400 CFM down to 600 CFM. The electricity savings was over $2,000 a day. And more importantly, it really created a culture change in the plants for awareness and energy cost, usage, and waste. So going through and getting people is part of it. So awareness training as part of the system approach to compressed air is very, very important. So how can CAC help with this? Well, presenting compressed air is not free. This is an operator awareness training that I just want to go through real quickly with you. It's customized to the site. It's meant to be delivered in 30 to 45 minutes, depending on content. So it's perfect for team meetings and toolbox talks. It's cost effective with several delivery options. It can be just downloaded for a cost in the plant facility. People put it together. It can be delivered by facility personnel and modified and assisted by a CAC instructor, or it can be totally done by a CAC instructor. The real key is it gives people awareness of what the cost is and what it is. So it's customizable. You have your rules of engagement. You have the overall picture of the plant that the people know that they come to every day. Your main three key things you want to get across to the operators is compressed air is very expensive. End uses there are different type of end uses. They can be appropriate, inappropriate, and they can be air leaks, and they really need to know and report those. Then also they are a key part of being able to save energy and save compressed air. So you go over the cost about what it is over 10 years. You can see electricity is the major cost of it. It defines some of the metrics, puts it in the facility cost so they know how much their actual cost is, what the hourly cost is, and what their production per unit cost is. It talks about what the system is, reviews the supply side, showing pictures of their air compressors, their filter dryers, their receiver tanks, the demand side, the typical components of demand, what there is in their actual plant. You can put in all different types of it, the effectiveness and efficiency of the system, how leaks are and what the leaks costs are. This can also be adjusted for the actual cost that they have, as well as this chart. This chart is customizable. It's done at 10 cents a kilowatt hour, but guess what? It can be changed for whatever the cost is. Then letting them know it's very expensive. So we talk about the 2 PSI equals 1%, and then the increase in leaks, and then reducing pressure drop is important. The overall efficiency of the thing, which you saw this slide before, and whether it's inappropriate or appropriate. So what are the actual appropriate and inappropriate uses? So gives some examples and then shows it. Is this something that works? Is this appropriate or not? Can it be done electrically? What about the diaphragm pumps? Can they be switched over, or can we put things like regulators on them? Different types of things you see in the plant for repairs. And these are actual plant pictures that we have. And you would take pictures for the actual plant that you're doing. Different types of things and losses that you have in there, which hose reels are notorious for leaks. And then wand and cleanup. So where can the improvements be made? How can usage be lowered? Talks about the 7-step action plan, which is right out of the fundamentals. This can be done without going to fundamentals, but the fundamentals gives the plant person the background to be able to do this awareness training. So it's highly recommended that they go through that to do this. But it goes through the 7-step action plan and where they can help. It gives them implement efficiency improvements that are done, some best practices that can be done, and what the keys are to the savings. So again, we're walking through the end users, everything that they should know to help them understand why it's so important and how they can go through and help save money and save energy. And then it gets back to the 3 things to remember, right back to them being the key, and then has a system owner. You can have the system owner, the CAC instructor, and then of course the Compressed Air Challenge website, and then question and answers. So again, this is a very good thing for going through and doing lunchbox talks and energy awareness, and fits into programs like ISO 50001 and the requirements for continuous improvement in education. And then process. I'm a big believer that for lasting energy efficiency, you have to make it part of what you do, not something additional to what you do. It needs to be integrated. So process integration, the stuff in blue is what we did at Ford, but really ISO 50001, ISO 14000. If you have sustainability initiatives, lean manufacturing, continuous improvement, world-class manufacturing, whatever your system is, putting it in. We had the Ford production system, and under that, each of the areas had their own operating system. So they had the energy management operating system, which was a set of how you went through and did it. And you put it into the plant facility goals and objectives, as it was part of the plant manager's scorecard, that energy was a piece that they had to go through and do. So again, driving what they normally do rather than something additional. So again, to maximize compressed air efficiency, always take a systems approach. And if you want to learn more, you can sign up for the AEE CAC Fundamentals of Compressed Air Systems webinar, which is being held in December. Or you can go to the Compressed Air Challenge website, where you can see the different training schedules, order the best practices manual. There's also great case studies, articles, fact sheets, and a DOE CAC source book that's a real brief source book on energy, and then other information that's done. So it's a great source for energy knowledge and training. And with that, I'll open it up to questions, and hopefully I didn't go too fast with it, but I did want to catch up a little bit on time to still try to have a little bit of time for questions and answers in the presentation. So are there any questions that anybody has? And I think, Sharon, that we have to go through and open it up for questions. We have to.
We need people to let's see if we go into attendees. We did have one or two people that had their hand raised at different times. So if you did have a question, raise your hand, and we can. If you have a speaker available, we can unmute you. Alternatively, if you have a question, if you'd like to type it in the question box, that will work also. I'm not seeing anybody with a hand raised, and I'm not getting any questions in the question box right now. Oh, no, one hand raised right there. Let me see, who is that? Okay, Godfrey, you're now free to speak. Go ahead.
Mine is not really a question, but to say that it was a nice presentation, and we'll definitely look out for the training that will be coming up. Thank you.
Well, thank you very much. I appreciate it. I'm glad you enjoyed it.
Okay, we do have one question coming in. We have Brian has asked the question, making conservation part of what you do makes sense. How do you get a plant manager to add an energy metric to his existing metrics?
Wow, that's a good question. One of the things that you can go through and do, because most of the time plant managers are either competing with other plants or, you know, outside of it with other companies, they're often very concerned and critical of the cost and profit and loss statements or overhead budgets. Many times putting it in the dollars that they can actually look at and save and what that costs them goes to a metric that they already have. At Ford, we were pushing hard enough that we were able to get it as part of the plant manager's scorecard, because we had corporate directives that basically said over a period of time we want to reduce by so much. So that was kind of a mandated, dictated one. So you get those from corporate. But if you don't, I think that going through and trying to put it in terms that they would get, that they need to go through and do anyways, which is going to be around the cost and the profit portions of it, is important. Anytime you can put it, if you can't get them to directly put it on their scorecard or as an objective, anytime you can relate it back to something they already need to do or have to do, it's an important part. Many times compressed air can cause production losses or production reduction, either by the quality or not having enough pressure that slows equipment down. Those are other things that if you can go through and actually be able to quantify that, it's important that you can go through and help them with the other objectives they have, which tie back into their scorecard. So trying to get them to understand, again, not only it's the right thing to do, but it's cost savings for them, I think hits and resonates better with plant managers and controllers than we want you to save compressed air and save energy. That answer the question?
Yes, thanks, was the response to that.
Okay.
Okay, and
Okay,
now
great.
we have a couple of people asking if the presentation will be available for the participants. I can say the presentation belongs to Joe himself, and that will be entirely up to Joe. Feel free to email him. I will, however, be sharing a recording of the webinar with all of you, so you will receive a link to that within the next day or two. So you are welcome to review the presentation from that recording.
Yeah, and as far as the slides, the ones I was telling Sharon that I have a concern with is the one for the awareness training, because what I actually showed you are the slides for the awareness training that you would get through the CAC, and that is CAC material. So that will be able to be ordered through the CAC anyways. The rest of the pieces and presentation I can go through and make available and can share. It's just the portions that are CAC related that I would have to remove from the thing. But as Sharon said, she'll also be sending the recording out so you can go through and review it, because I know, again, I went through a bit fast, but I wanted to go through and make sure we had the material and the time, given the fact that we started a little late as well. And as Sharon said, you can shoot me emails and questions as well. I think that you have my email address. If not, it's joeg@goe-llc.com.
Okay, we have one other person with a hand raised. We have, and forgive me if I pronounce this incorrectly, but Rezvat Azim. So I'm going to give you access to your microphone, and I cannot do that. Maybe you are self-muted, so I cannot release that for you. If you would type your question in the questions panel, we can address that one for you.
Or if you go to your however you've muted yourself on the board and unmute, that may work as well.
Yeah. No. Okay. Do we have any further questions in here? If you do have a question, if we are running out of time, then please feel free to go ahead and add it into the question panel, because I will download any queries and forward them to Joe. Somebody says, please, can you repeat your email address?
Oh, sure. That's JOEG, as in George, at GOE-LLC.com.
Okay. If there are
I guess the only other question I see, scrolling through it, Sharon, is question on CEUs. I think I read in the beginning that there's, in the email, that there's contact hours, not CEUs, for these webinars. Is that correct?
That is correct, yes. And if anybody is interested in that, we will not be sending out a certificate of attendance, but if you are interested in that or you have any questions regarding that, please email me and I will respond to you personally. Let's see. I think we may have covered all the questions. Oh, hang on, we got one here. Here we are. This is the person that we were trying.
Okay. One of the questions was how can we calculate efficiency?
And it says of the compressed air. Sorry.
Of compressed air. Well, there's a couple ways. There's the efficiency of the compressed air system itself, and there's the efficiency of the compressor. What you look at for the and both of them are similar. But what you look at is you look for the compressed air system. You're going to go through and look at what for the compressed air. Let's start first with the compressors. The compressors, you look at a kW input versus whatever your output is, whether you're doing it in CFM or whether it's cubic meters or bars or whatever you're using. That can be an indication of what the compressor input versus output is. So that gives you an idea of the total compressor. For the actual efficiency, going through and looking at the efficiency of the overall system, you can use total flow, but you have to be careful because if you have equipment like centrifugal compressors, they may be blowing off to atmosphere and you may not get a true efficiency, but you can take all of the kW per output as well. And then the final thing that I think is important is to go through and relate it back to production. I feel that you can go through, if you can put it into a regression tool, one of the ones that you can download anywhere, it's a Department of Energy, and the ENPI tool, it's the energy management tool that they have for intensity improvement. That particular tool, it's meant for ISO 50001 and for superior energy performance, but you can do it on a compressed air system. And what it does is it normalizes for production. And when you go through and can do a normalization using a regression, it makes it so it puts it on terms that it's not just an intensity, because often what happens is you run into issues with using intensity where you use a actual cost per product or BTU or kW per product. If you use anything like that, many times it gets related to sales more than it does actual production numbers, because often just increasing line speed on a production isn't costly because you've got the base load of all the equipment already running. So you can put it, if you want to get really sophisticated, you can put it into an actual calculation for a regression tool to do an overall system efficiency. But those would be the ways. So for both the compressor and the system, input power versus total output, the output of the compressor or total output into the plant. And then the second one would be going through and looking at the total energy over the time compared to production.
Okay, we have a couple of comments from Jim Travis. Jim wanted to emphasize that many utilities offer energy efficiency incentives for not only new energy efficient compressors, but incentives for repairs like air leaks under a compressed air retro commissioning program. It says contact your electric utility for availability of programs. And then we have one more question from Doug. Doug asks, how do you measure flow?
There's several ways to go through, several types of meters to go through and use for measuring flow. You'll use flow meters, usually a compensating flow annubar, hot wire anemometer type insertion flow meter is probably the easiest. You can also use vortex types, or they, for precision, many times they'll use pressure differential using orifice plates. I'm not crazy about the ones that are the insertion type that go through and use it based on pressure reduction or orifice plates, because you actually have a built-in pressure drop. And at Ford, I actually started removing unless it was for controlling the compressor, or if it was just for flow, I would remove the orifice plates because it was creating a 2 to 3 pound pressure drop, which cost me a lot of money just to go through and get metering. But there's a lot of different companies out there that have insertion meters. You can go through and do even hot taps if you can't shut the system down. But again, you need to make sure that it's pressure and temperature compensating when you go through and look at it, especially the temperature compensating piece of it. You want to be able to make sure that it can go through, because the flow characteristics of air changes with the, obviously with the density of the air as well. So unfortunately, CAC, we can't go through and give out names, but there's a lot of companies that have meters that are out there. You just make sure that the accuracy for both pressure transducers and for the flow is there, because again, you don't want to get any false readings for something that you're going through and measuring, either on a sampling rate that's too small, or for for one that may have a span of pressure over a large amount and have 1 or 2%, or 1 or 1.5% plus or minus efficiency on it. So you want to be careful about those when you're measuring it. So again, the ones I prefer are the insertion type anemometer, hot wire anemometers, or flow bars that don't have any pressure drop.
Okay, I don't see any new questions. Let me just double check. Nope, Doug just said thank you.
Okay, good.
And I think that may be it.
Okay, great.
Thank you very much, Joe. We certainly appreciate you being here this afternoon and for the wonderful presentation. Guys, Joe did give you his email address, so if you do have any further questions, please feel free to email him directly. And as I said, I will be following up by sending out the recording of the webinar in the coming days. I hope you all enjoyed it, and we thank you for joining us this afternoon. And hopefully you'll join us next month for our next webinar. So thanks, guys, and a special thank you to you, Joe.
Oh, thank you very much, and thank you for allowing me to put this on for everybody and for everybody's time.
Thank you, everyone. I'm going to go ahead and stop the webinar.